Now we will revisit Euler's formula and use it to study how to solve exponential and trigonometric functions involving complex numbers. So to begin with, I would like to just mention the formula here. E raised to plus or minus I theta is cos theta plus or minus I sin theta. So call it as equation 1, Euler's formula. Now let us try to express an exponential function involving a complex number. So to begin with, we will write it as e raised to z. Now remember, z is not a real number, it's a complex number. So instead of z, I have to write here e raised to x plus iy. Now this can be split as e raised to x into e raised to iy. E raised to x into e raised to I times y. So in this equation, we will use equation 1 and write it as e raised to z equal to e raised to x into cos y plus I sin y. So instead of e raised to iy, using equation 1, we have substituted it as cos y plus I sin y. So this is a way in which we can solve exponential functions involving complex numbers. As an example, let us try to solve this expression e raised to 2 minus I pi. So simply we can identify this 2 minus I pi with our familiar form x plus iy, and we see that x is 2 and y is minus pi. So using equation A, we can directly write it as e raised to 2 cos of minus pi plus I sin of minus pi. Now we know that cos of minus theta is same as cos theta, and sin of minus theta is minus sin theta. Anyway, sin of n pi is 0 and cos of n pi is minus 1 raised to n. So clearly this sin of any integral multiple of pi is going to be 0, and this is going to be cos pi, since cos of minus theta is same as cos theta, and cos pi will be minus 1 raised to 1, which is minus 1. Hence e raised to 2 minus I pi is going to be e raised to 2 into minus 1 plus 0, which is equal to minus e raised to 2. Yes, this is how we solve exponential functions involving complex numbers. Let us try to take our discussion further. Now we are going to define trigonometric functions involving complex numbers. In order to do so, I will have to import this Euler's formula, which is very much of importance, and we'll write it as e raised to I theta is cos theta plus I sin theta, and e raised to minus I theta is cos theta minus I sin theta. Now we are going to add these two equations. So on the LHS we have e raised to I theta plus e raised to minus I theta. on the right hand side, these two terms will get cancelled with each other and we will have 2 cos theta. So cos theta will be e raised to I theta plus e raised to minus I theta divided by 2. This is a very important formula. So equation B. Now similarly, we have to repeat the procedure, but this time we have to subtract these two equations instead of adding them. So e raised to I theta, which is cos theta plus I sin theta, and e raised to minus I theta, which is cos theta minus I sin theta. Now if we subtract these two equations on the LHS, we have e raised to I theta minus e raised to minus I theta. On the right hand side, since we are subtracting, these cos theta will get cancelled. This minus minus becomes plus and we have 2I sin theta. So we have an expression for sin theta now, which tells us that sin theta equals e raised to I theta minus e raised to minus I theta upon 2I. So this is the next important equation. Now these two formulae are very much general, so that means that we do not have any restriction on what theta we are going to have, whether it is real or imaginary, it does not matter. These two equations hold true in general, so we can directly extend and apply these two functions in the domain of complex numbers. So we now define the trigonometric functions involving complex numbers in the following way. We say that cos z, now remember z is a complex number, cos z equal to, now look at the equations B and C. We are just going to repeat them and going to write z instead of theta. Cos z equals e raised to I times z plus e raised to minus I times z divided by 2, and sin z equal to e raised to I times z minus e raised to minus I times z divided by 2I. These are the definitions of trigonometric functions involving complex numbers, and we have derived these two using the formula called as Euler's formula. Now we will try to solve some problems to get a flavor of it. So the simplest one of them is to prove that derivative of sin z is cos z. Now we all know from the calculus that this is the formula, but now we are going to prove this for complex numbers. So we will start our step by expressing sin z in terms of exponential terms. So sin z can be written as e raised to iz minus e raised to minus iz whole divided by 2I, which is equal to 1 upon 2I, which is a constant, so it comes outside the derivative, and then we are going to differentiate these two, and we already know that d by dx of e raised to ax is a times e raised to ax. Okay, so we will use this formula here and we will write e raised to iz into I minus e raised to minus iz into minus I. Now this I term can be taken outside and this becomes e raised to iz minus minus becomes plus e raised to minus iz. Now this I gets cancelled and we have e raised to iz plus e raised e raised to iz plus e raised to minus iz divided by 2. And we can see that this expression is nothing but the expression for cos z. So this is what we were planning to prove, that d by dz of sin z is cos z. Now as an exercise, you all should try to prove the converse. That is, you should try to show that d by dz of cos z is equal to minus of sin z. So this goes as an exercise. Now we will move ahead to prove some other results or to solve some other problems. So let us include a simple problem which tells us to find out the value of tan of I times log 2. Now this is an expression whose value any scientific calculator won't be able to give because it involves a complex or an imaginary unit inside it. So we will have the similar approach, tan of I log 2. Now this can be written as sin of I log 2 divided by cos of I log 2. Right. Now call it as some equation 1. Now we have to solve independently sin of I log 2 using the previously known formula. So we know that sin theta is e raised to sin z is e raised to iz minus e raised to minus iz by 2i, and cos z is e raised to iz minus plus e raised to minus iz by 2. So sin of I log 2 would be e raised to I times, now this entire number is z, so e raised to I times I log 2 minus e raised to minus I times I log 2 divided by 2i, which will be, now we have to skip a few steps and note that I squared is minus 1 and e raised to minus x is 1 upon e raised to x. So this I into I gives us I squared, which is minus 1, and minus log 2 is placed on the head of e. So this becomes e raised to minus log 2. So we can write it as e raised to minus log 2 can be written as 1 upon e raised to log 2 minus, now here I into I is I squared as it is, I squared is minus 1 into this minus sign gives us plus, so we will have here e raised to log 2 upon 2i. Now this is now a matter of simplification. E and log will get cancelled and we will have here 1 by 2 minus 2 upon 2i. Yes. Now this can be further simplified as 1 upon I times 2 into 2, which is 4, 2 by 2, which is 1, which is minus 3 by 4 into 1 upon I, which is minus 3 by 4i. Now we can do an adjustment. We will multiply and divide by I. So this I into I is I squared, which is minus 1. So this minus 1 will disappear and we will have 3i by 4. Yes, 3i by 4. Now this is just the half part, because now we have an expression for sine of I log 2 and it is 3i by 4. Yes. So the next step is to find out an expression for cos of I log 2. Again, we will follow the same method. Cos of I log 2 would be e raised to I times I log 2 plus e raised to minus I times I log 2 whole divided by 2. So using the same approach, we can have I into I becomes I squared, which gives a minus sign. So we will have a 1 by 2 here plus we will have a 2 here and whole divided by 2. So this is just 1 by 2 plus 2 is 1 plus 4 by 2 and whole divided by 2, which gives us 5 divided by 4. Yes. Now we have an expression for cos of I log 2 along with sine of I log 2. So now we can use tan of I log 2 equal to sine of I log 2 divided by cos of I log 2, which gives us 3i by 4 divided by 5 by 4. So 4 will be cancelled and we have 3 by 5 times I. So this is the answer. This is the answer of this expression. So this was a very lengthy problem, but we have to pay attention to each and every step. Now let me just clear this canvas and we will start with a fresh example. Suppose we are asked to find out or simplify this term sine of I log I. How much is the value of sine of I log I? So let us just rewrite the formula again. Sin z is e raised to I z minus e raised to minus I z whole divided by 2I. So in our case, z is I log I, right? So this gives sin z to be equal to e raised to I into I log I minus e raised to minus I into I log I divided by 2I, which is equal to, now again I into I is I squared, which gives us a minus sign, and we have 1 upon e log I minus I into I squared. With this minus it becomes plus, so we just have e raised to log I upon 2I. Now e and log get cancelled, so we have 1 upon I minus I upon 2I, which is equal to 1 upon I times 2I minus I upon 2I, which is, now this I into I is I squared, which gives us a minus half minus I goes with this I to get another minus half, so this will be minus 2 by 2, which is minus 1. So surprisingly, the answer of a very seemingly complicated expression called sine of I log I, sine of I log I is just minus 1. So let me clear the canvas again. Now, as a part of exercise, we should try solving these two examples. So first of them will be to prove this identity. Prove this identity. Sine squared z plus cos squared z will be 1. So how do we approach? In order to prove this, I will just give hints. So I have put boxes. Put the formula for sin z, put the formula for cos z, take squares. So let us just try e raised to iz plus, minus e raised to minus iz upon 2I, and here we will have e raised to iz plus e raised to minus iz upon 2. So this can be done. We have to take square of numerator in both these square brackets. So we will try to have a simplification of first bracket. So a minus b bracket squared will be a squared minus 2ab plus b squared. So yes, here we have e raised to iz squared minus 2 e raised to iz e raised to minus iz plus e raised to minus iz squared upon 4. 2 squared gives us 4, I squared gives us minus, so we will have minus 4 here, plus, now here we have a plus b bracket squared, and 2 squared gives us 4, so e raised to iz squared plus 2 e raised to iz e raised to minus iz plus e raised to minus iz squared. Now This just gives us, now we can put this minus sign to the numerator part so that the denominators of both these quantities become equal to 4, and we can combine them to write it as 4. Now remember that this minus sign is carried here, so I will write here minus e raised to iz squared. Here iz minus iz becomes 0 and e raised to 0 is 1, so this will give us just a 2 plus e raised to minus iz bracket squared plus, now we have to just write it as it is. This becomes 2 because e raised to iz minus iz becomes e raised to 0, which is 1, into 2 is 2, plus e raised to minus iz squared. So there is a mistake, let me correct it. Since this minus sign is carried to the numerator, this term which was positive becomes negative, this term which was negative becomes positive, this term which was positive becomes negative. Yes, now we can clearly see that these two terms get cancelled with each other. These two terms get cancelled with each other. 2 plus 2 gives us 4 divided by 4, which is 1, and hence we have proved the identity that sine squared z plus cos squared z is equal to 1. So we can keep on trying solving such problems. That is a matter of practice. Thank you.